XOR handles one parity block, enough for 8-5 to survive. Two failed disks need two equations, XOR alone can't derive. You need math that treats bytes as polynomials in a finite space. Galois Field GF of 2 to the 8. Rate 6's saving grace. Finite field, 2, 5, 6 elements inside. Every byte is a polynomial along for the ride. And with XOR, multiply through the field GF of 2 to the 8. The math at rate 6 wields two unknowns, two equations, solve for both disks lost. Galois Field, worth every computational cost. GF of 2 to the 8 holds exactly 256 elements, 0 through 255. Every possible byte value lives inside this field alive. Addition in this field is XOR. No carries, no overflow at all. Subtraction is also XOR. They are identical when bytes fall. 0 is the additive identity, XOR. When 0 stays the same, 1 is the multiplicative identity. Multiply by 1, back you came. Each byte maps to a degree 7 polynomial. Bits are the coefficients in line. The byte thousand is x plus 1. Bit positions define. The byte thousand 1 is x to the 7 plus 1. Reading high to low, 256 bytes, 256 polynomials. A perfect 1 to 1 show. Finite field, 256 elements inside. Every byte is a polynomial along for the ride. And with XOR, multiply through the field GF of 2 to the 8. The math at rate 6 wields two unknowns, two equations, solve for both disks lost. Galois Field, worth every computational cost. Multiplying two polynomials can exceed degree 7, leaving the field behind. We reduce modulo an irreducible polynomial to keep results in line. The standard polynomial for rate 6 is x to the 8 plus x to the 4 plus x to the 3 plus x plus 1. That is 0x11b at the core. Whenever multiplication overflows a byte, mod 0x11b brings it back. 1 byte in, 1 byte out. The field stays on track. The generator G equals 2 and GF 2 to the 8. The primitive root raise G to any power from 0 to 254. Unique values underfoot. Q parity uses G's powers, each disk weighted differently in the sum. G to the 0 times disk 0 XOR G to the 1 times disk 1. Here we come. P parity is XOR of all data disks. Equation 1 is set. Q parity uses GF multiplication with generator powers. Equation 2 to get 2 equations, 2 unknowns when 2 disks fail. Solve the pair. GF arithmetic is invertible. Every non-zero element has an inverse there. Substitute the known disks, isolate the unknowns. Using GF operations clean, the controller solves millions of these per second. with lookup tables in between. Pre-computed log and anti-log Controllers need dedicated chips to run at speed. Software RAID 6 taxes the CPU hardware. Acceleration is the need. Finite field 256 elements inside. Every byte is a polynomial along for the ride. And with XOR multiply through the field GF of 2 to the 8. The math that RAID 6 wields. Two unknowns, two equations. Solve for both dislost. Galois Field, worth every computational cost. Galois invented the field. RAID 6 put it to work. 256 bytes, polynomial math, irreducible. XOR alone can't derive. P is XOR, Q is GF. Together they solve for 2. Galois Field GF of 2 to the 8. Now you know what RAID 6 runs through.